Today we will discuss about measurement in quantum mechanics. Okay, it's a slightly difficult subject because there are subtleties in this thing, controversies over the decades, the collapse of how to justify, lots of delicate things, and we will not really enter into any of these delicacies. So I will give you the standard rules, okay, which seems to work very well, by the way, and now how to extend or how to justify or how to arrive at a comprehension of those rules is a different story. We will not enter into it. Okay, so one of the first postulates that we already discussed is that for every observable, physical observable, say, call it A, you can associate an Hermitian operator A. Hermitian operator. Okay? And that in the process of measuring the physical observable, what you will actually get from the apparatus is one of the eigenvalues of the operator. Okay? So I would recall you that, in fact, for any Hermitian operator, you have a complete set of states, set of eigenstates. Okay? So you have a basis of the Hilbert space. So in general, you have states phi n, such that these are eigenstates of A with eigenvalue an. And in general, each eigenvalue might have a degeneracy, so let me write here the fact that there is an extra index that in general has some values from 1 to some degeneracy Gn. Okay? If you put together all this phi and j, you have a basis of the Hilbert space. Now, expanding a general state, okay, at this point you can use the basis of any Hermitian operator you like, of any observable you like. As you know, you can form the projection operator over the eigenvalue an, which is this, but if there is degeneracy, then you have to add the j and sum over j from 1 to gn. Okay? So it's the sum of the projection over the different eigenvectors with the same an. Okay. You know that completeness of the basis means that you can always write the unity as the sum over n of this projection operator, Pn. Okay? So, which is written there. Very good. Which means that if I want to expand the state psi, I can always rewrite it as unity times psi, and I can re-express this as sum over n Pn times psi. Okay? And I can actually rewrite this as sum over n let me write it in this way: Cn times psi n, okay, where psi n is the essentially the component, okay, in the eigenspace of eigenvalue an but normalized. Okay? So you have to divide by this. Okay? So it's a normalized state in the subspace for which Pn is the projector. Okay. And so this is normalized and different eigenvalues are orthogonal. Therefore, if I ask you to calculate Cn, let's see, Cn is equal to what? It's psi n, psi, right? The usual trick. But psi n is this object. Well, let's write in fact Cn modulo square, which is what we need, in fact. Okay? So Cn modulo square is the modulo square of this, which I can write as, let's see, so this is psi Pn, okay, times psi divided by, I'm copying, divided by this, okay, and then I have to take the modulo square, okay, so that's the expression that I have there, and I want to show to you that, let's see, that this is in fact equal to, this is equal to the Pn psi modulo square. In other words, is the square of this denominator that you have there. Okay? To show this, I remind you that this object, this denominator here, can be written as psi Pn psi. Okay? You see the denominator here? But Pn square is Pn. So this is also psi Pn psi. And what about the object upstairs? The object upstairs is I think I used a wrong route to reach the object. Okay. This.
Yes, it makes sense, kind of.
It makes sense, but okay. But I have to fish out the thing. Let's proceed. I mean, there is a simple rewriting of this object and of this, using always that p squared is equal to p in such a way that you can prove that this is the object that you have. And at this point, I already proved to you that this object here is actually equal to psi Pn psi. Okay? We'll do it later, okay, with a bit of more calm. So the modulo square of this coefficient can be written in many ways, but in particular is the average of the projection on the state. Okay. And I will call this object, these are the projection operator, big P. I will call small pn, which is a probability in a second, will be the probability pn. We'll see later on. Okay? Now, the nice thing about this coefficient is that obviously, since the state is normalized, since psi is equal to 1, you can immediately deduce that the sum over n of the modulo square of Cn should be equal to 1. Okay? So somehow it is, in a sense, a legitimate way of saying that this is a probability. Okay? Should be a probability because, after all, it's positive or non-negative and normalized to 1. Okay? This is preliminary stuff. There is no measurement here. Simply saying I have a complete set of eigenstates of an Hermitian operator, then I can always write the projection of the determination operator, and I can re-express any state I want into an expansion into the eigen basis. Okay? Okay. Having said that, okay, let me just, so I will leave only these expressions written somewhere. Erase it. So I will leave here the expression for psi equal to sum over n Cn psi n, for psi n being Pn psi divided by its norm. Okay? And what else I need? I need, yes, I need Cn modulo square, which is a probability equal to psi Pn psi. Okay? This is all I need to proceed. Okay? So I erase here. Okay. Now comes the actual measurement postulates. So, if I measure the operator A on a state psi, the outcome of the measurement, okay, is one of the eigenvalues of the operator. So if I measure the angular momentum, I can get one of the eigenvalues to the angular momentum. Okay. I do repeat several measurements. So I do one measurement on psi and I get one eigenvalue. I repeat a second measurement on psi and I get a possibly different eigenvalue, but still one of the eigenvalues. Okay? So there is no deterministic way of saying I measure A and I will get this eigenvalue. Okay, so if I repeat the process many times, every time I will get one of the eigenvalues, but not always the same. Okay, is this clear? So I can accumulate statistics over the ensemble of identical measurements. Identical in the sense that I have prepared always my psi and measure always the same operator several times. So there is an ensemble of measurements that I do always in the same conditions, and I can accumulate statistics. Okay? So here there are the eigenvalues, and I just make a histogram of the different eigenvalues. Okay? Is it clear? So this is the experimental histogram that I can make after repeating many times. Then quantum mechanics tells us that although each eigenvalue is not deterministic, I can associate a probability Pn, okay, here, of measuring the eigenvalue An, okay, and I have an expression for that. And needless to say, it's exactly equal to the expression I gave you before. Okay? So this object, the Cn modulo square. The modulo square of the coefficient of the expansion of the state on the basis of the eigenvalues. This is precisely the probability that I will find a given eigenvalue in a set of measurements. Clear? Obviously, as I commented before, the sum of those things is 1, because essentially of this, and therefore it makes sense that this is a probability. Now, this, you realize, generalizes to an arbitrary operator what we already said about position. If you remember, we said that the probability density of measuring the particle at position psi was psi modulo square, which is simply the wave function x modulo square. Why is this the same thing? Because you see that the projection operator now on the state, say x, is simply xx, right? So if you reinterpret this thing, this is simply, or better, reinterpret this, psi x psi, okay, which is this, is precisely what's written there, okay? So you see, it is perfectly consistent with what we already said. Good. So this is the quantum mechanical rule to calculate the probability that I measure the eigenvalue an when I repeat measurements of the observable A. Rule number 1. But there is a rule number 2, which is the following. The collapse. Okay? So after I have psi, I have the apparatus which measures A. The apparatus gives as an answer an. Each time a possibly different thing. If I get an, then immediately after the measurement, the state becomes psi n. Okay? So in other words, it has collapsed to the projection of appropriately normalized on the eigenvalue that I have measured. Okay? So this is equal to Pn psi divided by the norm of Pn psi. Now, this is the most difficult thing to digest in some sense. Okay? Because it implies that the state abruptly changes. Okay?
Okay, so to clear, the cat psi contains all the information of the system, but since you are acting on apparatus A with the specific basis, that is the basis of the measurement, it collapses. The only information that remains will be the information.
Yes. Yeah. I mean, do not ask too many questions on the why, because as you see, I'm giving a rule that has been very much, I mean, that it is not liked by many great physicists, and it has been debated longly, so it's very hard to ask, why is this? It is, okay? Take it. Okay, good. These are the two set of things that you have to have in mind. Now, as a consequence of this, obviously, suppose that I ask you, okay, now I measure A, I obtain an, immediately after, I measure A again. Okay? In the first measurement, I was obtaining an with a certain probability Pn. Now I have this collapse state, which is this. I measure A again, my apparatus. Okay? Tell me what I will obtain. Only an is possible now, okay? Because the state is fully, in other words, if I rewrite the state in terms of, in this form, it is simply 1 times psi n, right? And therefore, the new probability of measuring an, okay, so it's an with probability 1. Okay? So once you have measured an once, the second measurement confirms always the first. Okay. Now let's do a slightly different thing. So suppose that I have measured, so here, AN, and I measure another operator, B. Okay? B has its own basis of eigenstates. So again, what are the possible eigenvalues that I will obtain by measuring B? One of its eigenvalues, okay? Bn. With a collapse. Now, you realize that there is a big difference if these two operators commute or not. Because if they commute, you know that I can always choose a basis which is compatible with both. So in some sense, I measure, for instance, suppose that they commute. Let's do the first case. A and B commute. Okay? So, in the first case, I know that I am within a block of states which have all eigenvalues AN. This is what the state lives in. Okay? So if I look at the A restricted to this little block, it's like this. Okay? So simply the general eigenvalues AN. Now, I measure B. Obviously, B is in general, suppose this is not the good basis of B, but I know that I can always make combinations of those states such that B will have certain eigenvalues, okay? And therefore I can calculate which are the possible values of B. But the important thing is that the second collapse, okay, now I have a new collapse, okay, to a state which is somehow still within the subspace, because I'm collapsing to a particular combination, for instance, of those states. So the new state is in the same block. Okay? Therefore, if I measure A again here, then I know that I will obtain again the same AN with probability 1. In other words, if I measure A, I get AN, and then I measure a commuting observable B, getting some eigenvalue of B, the measurement of A immediately after will confirm the result I got before with the same eigenvalue. Okay? So in some sense they are compatible. This doesn't disrupt that. On the contrary, if B does not commute, okay, then I will get one of the eigenvalues collapse into a state that has nothing to do, in general, with this block. Therefore, if I measure A again, I'm not guaranteed to get AN. I can get again one of the eigenvalues of A, which could be different from this. Okay? So it's like having, again, an initial state psi from which I can extract one of the eigenvalues with a certain probability. Okay? So this is the scheme of compatible measurement, or, in general, incompatible measurements. Okay? Good. Let's try to practice a little bit. No, before we practice, a little bit of theory of the expectation values. We have longly called the sandwich psi, A, psi, I have often said, are the expectation value. What do I mean? Okay, let's justify now this. This as an expectation value. Expectation value has a precise meaning in statistics. It means that I have some probabilities and I weight with the given probabilities the quantity that I am measuring. Okay? So, for instance, here I get this value with this probability. And therefore, statistically, the expectation value of the operator A as a statistical thing would be sum over n of AN times the probability of getting it. Is it clear? That's the standard statistical average, right? Okay. And now, let's see what Pn is. What is it? Here. This is sum over n of an, the modulo square of psi component on the projected state psi n. Let me rewrite this as sum over n, an. I write it as psi n, psi. Okay. Very good. This is the expression here. Let us look at this expression here. Okay? So I write psi a psi. So I express this object as sum over n of the coefficient Cn times the projector psi n. This. Okay? And I do the same here. So what I have is the sum over n prime and n of Cn prime star Cn psi n a psi n prime psi n. Is this clear? But these are by definition eigenvectors of A with an eigenvalue an. So this object here gives me an times psi n. Then these are different eigenvalues in general, okay? N and n prime. And I told you that eigenstate associated to different eigenvalue of an Hermitian operator must be orthogonal, okay? So the result of this thing is simply equal to sum, since there is a delta of n prime and n, a sum of Cn modulo square times an. Okay? But Cn modulo square is precise, so maybe there is not even any reason to write it. It's directly equal to that. Okay? So it's even shorter. Okay. If you want, you can also view this object here as being the spectral decomposition of A. As I told you, A will always be rewritten as sum over n of an times the projection over the state Pn, okay? And this is essentially what's written there. So this object here is nothing but the A that appears there. Anyway, you want to do it, there are several ways to proceed. You realize that these two things in fact coincide. So the expected statistical average that I get from the measurement is precisely the bra and cat sandwich of the operator. Okay? That's a very useful tool. Obviously, once important, in a measurement I never get this value. This is only the average of the measurements. In a measurement I always get one of the an. Okay? Good. Second, with the same tool, you can ask yourself, what's the variance? Okay? This is just a statistical concept again. As you have the expectation value, you can estimate the variance of your measurement. Okay? To estimate it, what you should do, what you should calculate is the following. you first calculate the values of the square, okay? Which are simply statistically this object, okay? And then you subtract, so the variance of A square is simply the expected value of the square of the quantity minus the expected value squared. Okay? So the square of this quantity subtracted from this quantity here. Now it takes very little to understand that precisely as this is equal to that, this object is equal to the square of the operator sandwiched on side. Okay? For the very same reason. Wherever there was an A giving you an, A square will give you an squared. Okay. Therefore, now I have a way to estimate the variance. The variance, which you know is positive, by the way, is simply equal to this funny thing. So psi A squared psi minus psi A psi squared. Okay? With this I have a precise way of defining the variance of two operators, of the measurements of two operators. Okay? And at that point you can prove a generalized Heisenberg principle. The product of the variance cannot be smaller than a certain quantity which is related to the average of the commutator of the two operators. Okay? This is the formula that I asked you to prove in one of the exercises. Okay? So it's a generalization of Heisenberg principle. In Heisenberg standard principle I have X and P there. X, P. And remember that the commutator of X and P is just I H bar. When you sandwich you get I H bar, the modulo square is H bar square. Okay? Okay. This is
H bar over 2.
H
Maybe
bar
it's
square for
without-
this.
Maybe it's without the square.
It is without the square. You're right. I mean, in the notes is square. There is no square. It's H bar over 2 if you include this part. Okay? Otherwise it wouldn't fit. Okay. Good. So this can be proven. It can be proven in a couple of ways. So either with using the Schwarz inequality or by following precisely the same steps we did for X and P. You choose, or maybe you do both, and try to realize that you see, if the two operators commute, this is 0, and therefore the lower bound there is 0, which means that you can, in principle, arbitrarily, nicely measure A and B. How? Well, you have some state, okay? I measure A and I get an AN. That state is a precise AN. If I keep measuring A, I will have a state of a very definite sharp A, no deltas, okay? So in some sense, after I have measured AN, this state here has a very sharp value of so the variance is 0. Okay? I'm not talking the variance on psi, the variance on psi prime, because I keep repeating the measurement and it's always AN without any variance. Okay? But if I measure two compatible observables, so I measure then B, the first time I will get some eigenvalue Bm. But if I keep measuring B, okay, I will always get the same eigenvalue. So again, a sharp value of B. So again, somehow a delta B equal to 0. And if I measure A again, since they are compatible, I still get AN. So once I have filtered somehow the eigenvalues with these repeated measurements, I have prepared states that have precisely well-defined values of A and B. In particular, the eigenvalues would be AN and BN. That's it. This is a state without uncertainty in the product. Okay, so the bottom of this thing is 0. And I can always do it because the two operators commute. Otherwise, every time I measure something or something else, okay, for instance, I have a wave packet, I measure X, I find it here, okay, very well localized in space. Unfortunately, the momentum is crazily ill-defined, and therefore, if I measure the momentum, I can find a very large spread of momentum, and so on and so forth, okay? Okay, good. So let us reconstruct, let's do a little bit of exercise with this technique in a particularly nice setup, which is that of Stern-Gerlach measurements of spin states. Okay. Good. Now, you will probably remember that, okay, if I have the Stern-Gerlach apparatus, okay, there is a precise direction in which the magnetic fields are aligned, okay, the things are deviated like this, and here I will have down states only, and here up speeds only. So as I told you, it's enough to create a hole in the screen to have a Stern-Gerlach filter, okay? So out of this filter, which you can consider to be just a black box with a hole, out of it, whatever you send in will come out, spin up, aligned with the filter. Okay? This is a nice device. Okay? Once I have prepared states of spin up, then I can ask myself what happens if I send those spin ups to a new filter. Okay? So let me just draw the new filter here. So I send this object to a new filter, but this time the filter, I can in principle rotate it so I will draw the filter by this arrow. Okay? So suppose that I rotate it around the XY plane at some angle theta. Okay? And I can ask you, what is the probability of measuring here a spin that exits the filter? Okay? Obviously, you realize that if this angle is pi, okay, then everything will be blocked, because somehow for this filter, this is a wrong state. Okay? So let me just do it in the usual setting. If I send to this filter the down, okay, then the spin is blocked, right? Because of the way it is constructed. So for the very same reason, if I send you the up to the filter being directed like this, then I will obtain 0 out. On the contrary, if I have the filter here at angle theta equals 0, then obviously the filter is compatible with the spin that we measure, and therefore the spin passes with probability 1. So here the probability of passing the second filter is 1, and here the probability is 0, right? The spin will be blocked. So the question is, what happens at any angle theta? So the rule is the following. what is the spin? So I'm measuring now spins at a certain direction, and I can ask you what is the spin eigenstate in the direction n that I want. Now, you remember that that is cos of theta over 2 times the spin up plus sine of theta over 2 times the spin down. You remember? I am on the plane, so there is no factor e to the I phi there, just to simplify things. Okay, so what does quantum mechanics tell me? That measuring the spin here, I will now always obtain, first of all, one of the two eigenvalues, but the probability that the spin will be actually aligned to this, okay, so up in here, is given by this magic 7, okay? So the probability that this object will pass, okay, is equal to the modulus square of phi n with the state psi, this is the state psi that I send to the apparatus, okay? So in this way of seeing the thing, I've prepared with the first Stern-Gerlach a certain state psi, and then I have sent it to some measuring device to measure the spin along a different direction. Okay, so this operator is a spin along a different direction, which has its own eigenvectors, okay, which are not up and down. So the object, obviously, is the modulus square of this, and the result of this is cos square of theta over 2. Okay, so for theta equal to 0, probability 1. For theta equal to pi, probability 0. Anything in between, here it is the probability. Okay? Clear? Now, let me just give you a simple analogy. Because this might seem a bit strange. Let me give you a simple analogy. And the analogy is very, very classical. It is, in fact, with polarizer filters. Okay? So, in fact, it happens that I have here the whole apparatus to do the experiment with you. Let's try it. Okay? Just to have a little bit of fun. Okay, these objects here, okay, the Polaroid lens, are polarizer for light. They are a little bit like this, the filter I'm talking to you, but they simply select the electric field of the electromagnetic, of the light that passes, okay? So in particular, just remind you that the polarizer, okay, is made of objects that are elongated, so molecules like this, and if the electric field oscillates in this direction, is absorbed. If the electric field oscillates in this direction, is not absorbed, okay? So if I put a screen like this, and I send light, then the light, sorry, the drawing is not particularly in perspective, the light that is oscillating horizontally, okay, along the molecules is absorbed. The light, okay, whose electric field oscillates vertically, comes out, okay? So what comes out of the filter is light that is vertically polarized. Okay, good. Then I take a second filter, okay? So suppose that the electric field was in a certain direction, say the vertical direction, and I put a second filter. So here is the new direction, okay, of the second filter. Then you realize that essentially what you have to calculate is the component of the electric field coming out of the first filter in the good transmission director of the second filter. And needless to say, the intensity that comes out is precisely the cos square of this angle. Okay? So if the angle is 0, the two polarizers are aligned, you get the same intensity. If the angle increases, you get less and less until at pi, you get 0. Okay? And you see that the angle between the two polarizers, call it alpha, plays the same role of this theta over 2. And the vertical polarization plays the same role of the spin up. Okay? So there is a precise analogy between the two things. I don't think we will manage to do it.
This theta angle that we have.
Okay, let's see this.
It's impossible to see here. So we don't do the experiment. It's too faint. Yeah.
The theta angle that we have is, in general case, is the relative angle between two.
Yeah. Of course.
So if we make this kind of apparatus that, for example, the first filter is like this polarizes the spins this way, then there is a next one slightly tilted, and so on. It makes a one whole circle.
Yeah.
At the end of this apparatus, will we still see the output of the spin?
I'm not sure I understood the full set of measurements. Maybe we have to sit down and try to do the calculation. Typically, answer to questions of setup of quantum mechanics do require a little bit of thinking. So do not expect that in a second I will calculate for you the thing.
Is it like you are putting another next
It's like
filter that is
first
like
filter,
greater
then
theta?
it's the second filter,
Yeah.
third,
Okay.
fourth, and
Every filter the theta
Yeah,
is
you can calculate what is the combined probability.
But at the end of the result,
Yeah.
we will still have an output. Ignoring the fact that in the beginning the spin was filtered in zeta positive direction.
Okay.
And
It could be.
after
Yes.
this whole spin it can be.
I see what your point is. We can calculate. Maybe you are perfectly
Is it
right.
not like, for example, the theta for each measurement, the
Theta can be
theta goes
infinitesimal.
to pi?
Sorry?
The theta will if the theta for each measurement the theta slowly approaches to pi.
It doesn't matter because this is the
So will the probability be approximately going to 0?
no.
I don't know how to do the calculation by heart quickly, but certainly it is a well-posed exercise that we can do.
Yeah.
Okay.
I don't think so. I don't think that it will go to 0 because theta angle is relative angle between two
Between
filters.
the two.
So if the angle between first filter and second filter is infinitesimally small, not pi over 2, not pi over 2, then you can do like this a bit shifted, then this is a bit shifted, and this a bit shifted. But the relative angle between the first filter and the second filter can be arbitrarily close to pi over 2, and you.
I will try to do the calculation myself. It's a good suggestion. Putting several of this one after the other. I just wanted to show you. Okay, there's no need. I mean, the thing is that if you do the experiment with a lamp and you put the two Polaroid lens, just one after the other aligned, you see still the light, but as you turn it to pi over 2, you see nothing.
It can be seen with the phone screen.
Well, in fact, with the phones and with the, if you go with the sunglasses to airports and you look at the LCD screens, you see nothing because maybe the light of the screen there is polarized in a certain direction and your lenses are orthogonal. You see very dark thing. Okay, so you have to turn on your head to see the thing. In any way, this is exactly the same effect. Okay, so it's pretty much like the polarizer effect. Okay, that you have with the standard optics filter. And by the way, much of what we say here about spin, Stern and Gerlach is routinely done in quantum optics lab with photons. Okay, so for instance, creating entangled pairs of spins. Okay, to do whatever, quantum cryptography, violation of the Bell inequality, and blah, blah, blah. All these things are done with photons, and the role of the spin is the polarization of the photon, okay? Never mind. Let's move. Let's move to what? Let's see. This is our first somehow measurement. Now, remember there is a collapse. So at the exit of once this spin has passed through the filter, and it does so with a certain probability, which you can calculate, cos square over 2, here the spin has collapsed into being in that direction. Okay? So in some sense the new wave function is precisely this. Okay? And you can do several other things to this thing, as he was honestly suggesting. So this is a way, but for instance, you can use to prepare spin along x. Okay? So if I want to prepare the spin along, say, the x-axis, all I need to do is to first prepare, say, spin up. Okay? And then send them to a second filter, which has the axis along the x direction. So let's put it here. Okay? Then when it exits from the second screen, the object will be plus 1/2 along x, which is the state that you can look there. Let's see what it is. The plus 1/2 along x is equal to pi is equal to theta is equal to pi over 2. So this is the cosine of pi over 4 up plus the sine of pi over 4 down. Okay, but sine and cosine of pi over 4 are just 1 over root 2. Okay? So here is the state that you have prepared, starting from an upspin and making it pass through a Stern-Gerlach filter. Okay? In this direction. Obviously you might say, but what about having, say, 2 holes? Okay, so suppose that here I do have only 1 hole and I prepare the up. But in this second filter, I could have really the second hole open. Okay? At that point, I would see with probability 1/2 spin coming out of the first hole, and there will be essentially this state, and with probability 1/2 the other eigenvalue of the spin along z, which is minus, okay? And you can show that the minus state is exactly equal to this, okay? So they have a slightly different phase, and you can prepare, well, just take theta equal to minus pi over 2. You see that you change here the 1 over root 2 into minus 1 over root 2. Okay? Good. So, what else can we play? Several things. In fact, I plan, when we'll do our tutorial, to do a little exercise about what happens if you prepare pairs of spins in a singlet state, which they are called entangled state, and you measure the spin at 2 faraway points in 2 different directions. This is a very instructive exercise that shows a non-local aspect of this of quantum mechanics. Very puzzling. In fact, Einstein pointed out that it was a paradox and it was against the rule, the law of reality and things like this, but nature seems to be rather bizarre, and people doing quantum optics experiment in Innsbruck, for instance, in '98, but even before in Paris, they have confirmed that quantum mechanics is a bit strange. Okay, so it doesn't conform to the inequalities that you would expect in classical physics. They are called Bell inequalities, and it violates those inequalities. And therefore, I mean, there is a lot strange stuff behind. Okay, good. What else can we do?
But I think this already answered Mikhail's question, because apparently when we go on the y-axis, it already forgot where it came from, right? Now the probability is like, it doesn't know where it was before.
I mean, of course, once you have collapsed, okay, on this object here, for instance, it might have come from a down spin. Okay? So the down, okay, also, if you measure with half probability, will give you a spin along plus x coming out. So, yes, after the collapse, I've somehow forgotten about where it came, partially at least, where it came from. For instance, in this case, there was a total symmetric probability of getting still 1/2 from the down, okay? So if I create this state and I ask you, what was the state before the measurement?
Yeah.
That's not, okay, could be up or down. So it's not a priori guarantee. So every time just think about the question that you ask. I don't know if this is this connected?
Yes, I think yes, because he was saying make a small angle, but even without small angle, if you just make 90 degrees angle, then it forgets that.
No, maybe his argument was about precisely small angle. So I still have to sit down and think more carefully. But maybe he was suggesting that with small angles you get something funny, something different. So I don't know. I have to sit, think, and calculate.
Just to restate the problem, initially we had only spin-up states.
Yeah.
One spin-up state. Then we
Yeah.
had a system of filters. And is it possible to get as an output spin-down with the filters, just doing something?
It is impossible or possible?
Or possible or impossible.
Okay, so question is calculate and see what is the probability. Okay, yeah. This is an exercise. I mean, it's a sequence of measurements.
Yeah.
Okay, the probability of the first measurement, okay, is given, and at the outcome collapse. Then again, the state can be further.
Yeah.
It is the relative angle that matters. You can proceed and calculate what is the probability that at the end you have
only spin down state.
Yeah. Nice exercise. I'll note it down, but don't ask for the question immediately, because you have always to sit down and think carefully. Okay, there is one simple thing. Suppose that I prepare. Okay. Let's do a simple exercise, and then we move. Suppose that in some way I prepare the state psi of, say, plus n, okay? Which is what I wrote before, okay? So I have a filter, and the filter is able to select at the end this state. Now I can ask you, try to measure Sx now. Okay? To measure it, obviously you install a new Stern-Gerlach apparatus now along the x, right? Obviously you will get the spin here or there, okay? So you better have two holes, otherwise one exit and the other. So you can measure spins either there or there with a certain probability, okay? So you can calculate what is the probability P of having plus 1/2 along x, okay, on this state here. And it is simply equal to, again, the overlap square between the state that you have at the entrance, which is in this case this psi n, okay, modulo square. And the probability that the object ends into the minus 1/2 hole is this one. Okay. And we can calculate these numbers. We have already calculated, by the way, the probability that if you measure the z again, so the probability that you will measure plus 1/2 along the z, we said is equal to plus 1/2 z psi plus n. Okay? How much is this? The modulo square, we calculated it already, is the cos square of theta over 2. And the other is the minus 1/2 z is the sine square of theta over 2. Given that, I could ask you, what's the average value of the spin along sigma? Okay? I measure plus 1/2 with this probability and minus 1/2 with this probability. Okay. So the average of Sz is equal to plus 1/2 with probability cos square over theta 2 and minus 1/2 with the probability sine square of theta over 2. What is the result? Let's see how fresh is your trigonometry. Cos square of alpha minus sine square of alpha.
Cos theta.
Cos theta.
Cos theta.
Okay.
Yeah.
In other words, it's the cosine of the twice the angle.
Yeah.
Okay. So this is 1/2 the cos theta. Okay. So the average SD is 1/2 cos theta. Now let's calculate these two numbers. And calculate the average Sx. Okay? First number. Let's do an exercise. This is essentially 1 over square root of 2, 1 over square root of 2. I'm now using to calculate the scalar product two-dimensional vectors, okay? Because it's simpler. So this is, what is it? Cos theta over 2 and sine theta over 2. Okay? So it's this scalar product modulo square that I have to calculate. So it's 1 over square root of 2 cos theta over 2 plus sine theta over 2 squared. Okay? That's the object that I have there, and this object here, similar calculation, I have just a minus sign here. It is equal to 1 over square root of 2 cos of theta over 2 and minus sine of theta over 2 square. Okay? So please exert your abilities in trigonometry to do 1/2 this minus 1/2 this. Okay? And you should find that the result is 1/2 sine theta. Okay? In other words, the average value are precisely what you expect from, say, if this n is in this direction, okay? So the average, this is theta, the average sigma z is cos theta, and the average sigma spin x is the sine theta. And if I had here the famous phase e to the I phi, so the n was in a given direction n, I would measure this to be sine theta cos phi, and the other side, the y, sine theta, sine phi. So the average value of the measurements are very simple to interpret classically. They are just cos theta, sin theta, cos phi, sin theta, sin phi, as in the spherical component. So please try to do this exercise to practice a little bit with these calculations, and you will discover that average values are classically simple, while individual measurements are not that particularly simple to understand. Okay? So in other words, what I told to you is that if I measure on the state n the spin operator, the result of this expectation value is precisely along n. Okay? So the state n there somehow determines what is the average of the spin. Alright? Good. So let's close for the time being, although there is a lot of things, including suggestions from the audience, that you can do with these are probably the simplest setting in which you can do interesting combinations of non-commuting. Remember, spin along different directions do not commute, so they disrupt each other, as you were pointing out. In particular, it's impossible to somehow measure simultaneously the spin in two different directions, in some sense, because they do not commute. And I told you that these are not compatible observable. Okay, let me just finish with the introduction to the hydrogen atom. We have to switch to hydrogen atom, unfortunately, but we'll get back to spin and to similar exercises later on. Okay, so just the starting of the hydrogen atom story. This is by far the most complicated problem we will do in the course, but we have essentially all the ingredients to do it now. So the trick is separation of variables. We have seen separation of variables in simple circumstances. Now we will use it in a more sophisticated manner. First of all, okay, the problem is that I have some nucleus of charge, say, plus Z, E, and only one electron somehow. Classically, the electron would orbit around the nucleus. And if I ask you what is the Hamiltonian, then you would say, okay, let me call P1, say, the coordinates, whatever. This is, I call it 1, and this I call it 2. So it's P1 squared divided by 2m1, the mass of the nucleus, say, plus P2 squared, the 1 over 2m2, the mass of the electron, minus Z E squared divided by the distance between x2 and x1. Okay? That's the Coulomb interaction between the positive nucleus and the negative electron. Obviously, to this I have associated the x1 and p1 pairs of operators, and to this I have associated x2 and p2 pairs of operators. Okay? Now, when you do the Kepler problem, the two-body problem, you know that center of mass is the right thing to do, right? Because the center of mass just moves with constant velocity, because there is no external force, it's all internal force. So we have to try to move to the center of mass coordinates and relative coordinates. And here comes the first thing. So first of all, what is the center of mass coordinate? Well, we know very well from classical physics, that's it. Okay? M being the total mass. what is the canonically conjugate momentum? It's obviously the total momentum, P1 plus P2. Now, classically, it's obvious. Quantum mechanically, we have to verify that if I take R alpha and I commute with P beta, I get I H bar delta alpha beta. Okay? Now, let me just okay, here there are lots of indices, but let's do it anyway. So here I have M1 over M, say X1 alpha plus M2 over M X2 alpha, commutator with P1 beta plus P2 beta. Okay? Now, obviously, I didn't tell you, but x1 and P2 commute, because this takes derivative with respect to 2, and x1 doesn't care, and vice versa, these two commute. So I have to take only commutator of these two objects. And you realize that this gives you I H bar delta alpha beta, this gives you I H bar delta alpha beta. You put the two things in common, M1 plus M2 is M, so this thing cancels, and therefore there comes the result. So these two objects, center mass and total momentum, are quantum mechanically nicely canonically conjugate. Then, if I ask you, tell me the relative coordinate, how did I indicate here? X. Well, that's simple. X2 minus X1, okay? If I have this, okay, this is, say, X1, there is a common origin, this is X1, this is X2, okay? X is this, the relative vector, right? X2 minus X1. Clear? Okay, this is clear. What is a bit less obvious is what is the relative momentum. Because here, I'm sure you would be tempted to say it is equal to P2 minus P1. Would you? What you would say? What is the relative momentum? Don't feel afraid. I mean, it looks very natural, right? It's wrong. Why is wrong? Simple. Okay, let's see. It should, first of all, be same thing. So, x2 alpha minus x1 alpha, commutator with p2 beta minus p2 P1 beta. Okay, so let's do the commutator. So this with that, and this with that. So the result is I H bar delta alpha beta, minus and minus is a plus, plus I H bar delta alpha beta. So this is 2 I H bar delta alpha beta, not nice. Okay, now one could argue on how to obtain a solution. Just put two constants here and make the constant nicely fitting the end result. But let me just give you the outcome. Here it is. M1 over M in front of P2 minus M2 over M in front of P1. Okay? If you check, what happens now is that here I have M1 over M in front of P2, and here I have M2 over M in front of P1. Now we do the same calculation. This object comes now with M1 over M, you see? And this object plus, but now M2 over M. Okay? And because of that, the sum is just now 1. Okay? You might say, but apparently the thing works even if you exchange, and here you put m2 over m, and here m1 over m. The algebra will be the same, right? But you want also to make sure that these two objects commute, okay? So you want also to impose that R component alpha and P small p component beta is equal to 0. And if you check, this is the way to make them commute, because you see there is the precise commute. So 2, okay, and 2 go together, and here you get m1 times m2, and in the other you get minus m2 times m1. If you exchange these two, you get m2 squared minus m1 squared, which is not the same thing, okay? So you have to put the coefficient in the right way so that they cancel for this. Okay, so that's the solution. Good. So I know relative coordinate and momentum. And by the way, you know that you can express the total Hamiltonian in this new variable precisely as in classical physics as total momentum squared divided by twice the mass plus relative momentum squared divided by twice the reduced mass minus z e squared over the relative coordinate. Okay? So notice total kinetic energy of the center of mass, but no appearance of the center of mass position. Obvious, right? Because you can move the whole thing whatever, and the energy is the same. And the relative motion is governed by only these two variables. Okay? So starting from, say, R, P, X, and P, I really have separated the problem in two parts. The center of mass part is very simple. It's plane waves. You see, it's a free particle type of thing. So what is the wave function associated? Well, it's a plane wave. Not particularly crucial to the story. The whole story is about the relative motion. So I want to understand what is the wave function of this. So from now on, I will denote this to be the hydrogen atom Hamiltonian. It's evident that I'm forgetting about this, and this is in principle the relative motion which I look at. So the goal is to somehow be able to diagonalize this problem, so to find, so this is p squared over 2 mu minus z e squared over x, psi of x equal to e psi of x. So this is the goal. Solve the Schrödinger equation, which is now a three-dimensional potential with spherical symmetry, and here you have the Laplacian, three-dimensional Laplacian. We have to solve this problem. Okay, now we will do that by using the fact that in the Laplacian in three dimension, the angular momentum square enters, the total angular momentum, and therefore we will separate variables here into a radial function, not confused with the center of mass. This is the radial function times spherical harmonics. Okay? So we will use this separation of variables in radial coordinates and spherical harmonics, and this reduces our problem to a purely radial, somehow one-dimensional Schrödinger equation. Okay? And at that point, we will be able to solve it exactly, because it's a one-dimensional, very peculiar problem. So not every one-dimensional problem, obviously, can be solved, but that problem can be exactly solved. Okay? So that is the plan of what we will do next time. Good.